വാര്യർ അവതരിപ്പിക്കുന്നത്.
ഈ സാങ്കേതിക വിദ്യയെക്കുറിച്ച് വിശദീകരിക്കാനായി ഡോക്ടർ തൃപ്തി എസ് വാര്യറിനെ നിറഞ്ഞ കയ്യടികളോടെ ഈ വേദിയിലേക്ക് ആദരവോടെ ക്ഷണിച്ചുകൊള്ളുന്നു. അടുത്തതായി നമ്മുടെ ബഹുമാനപ്പെട്ട അതിഥിയെ ഈ സദസ്സിന് ഔദ്യോഗികമായി പരിചയപ്പെടുത്തുന്നതിനായി ഇലക്ട്രോണിക്സ് ആൻഡ് കമ്മ്യൂണിക്കേഷൻ എഞ്ചിനീയറിംഗ് വിഭാഗത്തിലെ പ്രൊഫസർ അഞ്ജു ടീച്ചറെ ഈ വേദിയിലേക്ക് ആദരപൂർവ്വം ക്ഷണിക്കുന്നു.
എല്ലാവർക്കും നമസ്കാരം. നമ്മുടെ ഈ സെഷനിലെ മുഖ്യ പ്രഭാഷക ഡോക്ടർ തൃപ്തി എസ് വാര്യരെ ഈ സദസ്സിന് വേണ്ടി ഞാൻ ആദരപൂർവ്വം പരിചയപ്പെടുത്തുന്നു. ഡോക്ടർ തൃപ്തി നിലവിൽ കൊച്ചിൻ യൂണിവേഴ്സിറ്റി ഓഫ് സയൻസ് ആൻഡ് ടെക്നോളജിയിലെ ഇലക്ട്രോണിക്സ് വിഭാഗം അസിസ്റ്റന്റ് പ്രൊഫസറാണ്. പ്രശസ്തമായ IIT മദ്രാസിലെ കമ്പ്യൂട്ടർ സയൻസ് വിഭാഗത്തിൽ നിന്നാണ് ഡോക്ടർ തൃപ്തി PhD കരസ്ഥമാക്കിയത്. വിപ്രോ ടെക്നോളജീസിൽ സീനിയർ പ്രൊജക്ട് എഞ്ചിനീയർ എന്ന നിലയിൽ സേവനമനുഷ്ഠിച്ച വിലയേറിയ വ്യാവസായിക പരിചയം ഡോക്ടർക്കുണ്ട്. FPGA അധിഷ്ഠിത സിസ്റ്റം ഡിസൈൻ, ഡിജിറ്റൽ സിസ്റ്റം ഡിസൈൻ, RISC-V പ്രോസസ്സറുകൾ, AI/ML ഹാർഡ്വെയർ ആക്സിലറേറ്ററുകൾ, മെമ്മറി സിസ്റ്റംസ്, കൂടാതെ ആരോഗ്യ രംഗത്തെ സ്മാർട്ട് ഉപകരണങ്ങൾ, ബയോമെഡിക്കൽ സെൻസറുകൾ എന്നിവ ഉൾപ്പെടുന്ന വിപുലമായ ഗവേഷണ മേഖലകളിൽ ഡോക്ടർ ശ്രദ്ധ കേന്ദ്രീകരിക്കുന്നു. ഭാരത സർക്കാരിന്റെ MIT, TST, റൂസ തുടങ്ങിയ ഏജൻസികളുടെ ധനസഹായത്തോടെയുള്ള പ്രധാന ഗവേഷണ പ്രോജക്റ്റുകൾക്ക് ഡോക്ടർ തൃപ്തി നേതൃത്വം നൽകുന്നു. ഇൻകോ സെമി കണ്ടക്ടേഴ്സുമായി RISC-V പ്രോസസർ ഡിസൈനിൽ വ്യാവസായിക സഹകരണം എടുത്തു പറയേണ്ട ഒന്നാണ്. വിവിധ വിദ്യാഭ്യാസ സ്ഥാപനങ്ങളിലെ പാഠ്യപദ്ധതി രൂപീകരിക്കുന്നതിൽ ഡോക്ടറുടെ പങ്ക് വലുതാണ്. MG യൂണിവേഴ്സിറ്റിക്ക് കീഴിലുള്ള സെന്റ് ആൽബർട്ട്സ് കോളേജ്, കുസാറ്റ് ഇലക്ട്രോണിക്സ് വിഭാഗം, പാലായിലെ സെന്റ് ജോസഫ് കോളേജ് ഓഫ് എഞ്ചിനീയറിംഗ് ആൻഡ് ടെക്നോളജി തുടങ്ങിയ പ്രമുഖ സ്ഥാപനങ്ങളുടെ ബോർഡ് ഓഫ് സ്റ്റഡീസുകളിൽ ഡോക്ടർ സജീവ അംഗമാണ്. ഇത്രയും വിപുലമായ അക്കാദമിക് വ്യാവസായിക പശ്ചാത്തലമുള്ള ഡോക്ടർ തൃപ്തി എസ് വാര്യരെ ഈ സെഷൻ നയിക്കുന്നതിനായി ഞാൻ ആദരപൂർവ്വം ക്ഷണിക്കുന്നു.
ഷോർട്ട് ഇൻട്രോ ചോദിച്ചത് നേരത്തെ എഴുതിയ ഒരു സാധനം കൊടുത്തത് അത്രയും കൂടുതലായിട്ട് അഭിനന്ദിക്കുന്നില്ല. താങ്ക് യു വെരി മച്ച്. ഇൻട്രൊഡക്ഷൻ ഞാൻ ജസ്റ്റിഫൈ ചെയ്യുമെന്ന് എനിക്കറിയില്ല. Thank you for calling me here. I'm happy to be here and talk about what I'm doing. So whatever I present here is part of the work that is being carried out in our lab with the help of in collaboration with that startup called Infosys. So insights from that and some work that we have done is presented in this. So we are going to discuss about RISC-V architecture, and if you look at any new activity that is happening in processor design, you will see that there has been a transition from traditional Intel architectures towards open source architecture in the last decade, and RISC-V is one such architecture which people are predominantly using because of its many features that we will be highlighting in the initial couple of slides. So and then I will be discussing certain aspects of design that will help us to extend this design to any particular domain specific designs. So that's why my general talk outline will be consisting of just basics on this, why we go for domain specific architecture, and then application that we are looking at. I have talked about cryptography. I will touch it or not touch it based on time I have, but I will discuss about ESP and AI architectures, that is here. Okay, so and then I will give our summary of what we feel can be used in RISC-V for such applications. So RISC-V is an open source ISA. ISA is instruction set architecture, and all traditional architectures that we have been using from the start of processor design. Initially, the first one was Intel 4004, and so those ISA instruction set architecture is the basics to design any computing system. So what we will be designing for a processor is, you have a list of instructions that a computer will be executing, and then a hardware which is going to execute those instructions. And when these instructions are belonging to any particular, say, intent, and if you want to build a processor which is implementing that instruction, we have to get the license for it so that we can use it. So, whereas when you say open source, it means that a common guidelines and ISA structure is available to you, and you can implement your own version of your hardware that is going to execute this ISA. That is what open source means. So, tool being open source, you are all aware of, right? So, open source tools, you don't need to pay or get a license, and so it is free for you to use. Similarly, this ISA this instruction set architecture is a combined is a set of instructions grouped into different versions that we will see, that will allow you to implement a processor, and then there is a group working on it to always extend the instruction and then give you what is the performance of a processor implementing this instruction using applications also. So you will know if I have implemented a design which is following this any particular group of ISA of this file, and I run an application and see that I take 100 cycles. If there is somebody else who has implemented in 90 cycles, it means that you can design it better, right? You can design it better and come up with a design which is going to be better than the current design. So this gives you the freedom to come up with your own design free of cost, and then change it also to according to what application you are targeting. So how this this is the instruction set architecture is a free open source, and you can modify it. So it's modular in nature, you will see, and then you will be able to modify it to according to your needs. To design not the ISA, the design can be modified. You can pick and choose what instruction you want to implement based on your application. That is the advantage of instruction set architecture. So can we design? So again, we design for an application with a cost of power, area, and performance. So you will be able to customize your design based on your requirement. So even if you take an ARM ISA, it is defined. Any program compiled in any ARM core should run in any other ARM core. That's how it is. Here it is not the case. You don't need to support all instructions if you don't want it. That is the advantage of this. So this architecture. So ISA comparison that I have done here is with ARM, x86 and RISC-V. So what you see here is that there are many different groups of instructions, and vector instruction sets are inside the chip is available in all of them, but then no need for architectural license, no need for no core which is commercially sold with license for RISC-V. You can do yourself your own work on it, and then you will have so core and IP, everything is open source, but that is not the case. That is not the case for x86. For ARM, you have the core available to you as an IP which you can buy. Again, you have to pay and buy. So these are the points why we will go for RISC-V architecture. So as a researcher, if you want to work on a standard instruction set and come up with your own design of a processor, this is something which is a good start. And in you will find a number of standard designs which support it. You don't need to start from scratch. You will be able to get designs all with basic instruction set available to you, and then you will be able to modify it to do whatever you want it to. So that's why we go for RISC-V. So here there is a comparison with other open source ISAs which are available. So RISC-V has a comprehensive set of large instruction support. So as is shown here, you will have, it's a compact code, and then you have floating point, then you have 32-bit address support and 64-bit address support, and then software supports GCC, LLVM, these are compiler supports. These compilers are slowly starting to support this ISA. So these are the in terms of other ISA, why will we go open source ISA? Why will we go for the same pointer? So not only are researchers going there, companies are using this file to customize their customize hardware for their application. That's also the case. Okay, so these are so now if you look at instruction set, why is it modular? Is what I'm trying to tell you here is if you have a base instruction set, which is generally we all know it's integer instruction. That's what we all learn first. So that's the base. Some 42 instructions are there, and it has been shown that almost all applications can be executed using this 42 instructions. Just normal applications can be executed using these. Now, other than this, there are extensions that are there. Some of them are standards and some of them are non-standards. So, what is the difference? Standard instruction set are instructions set which has been properly. People who need those instructions will make a list of instructions and they put it. So initially it will be non-standard, and when large number of people working in the same area give a confidence, all will have their own list similar to that, and then finally they will ratify it in the form of standard instruction set. So initially it will be non-standard, and once a group of people working in their areas, so there is a group, very powerful risk group, and they decide on what should be when an instruction extension will be made standard. So whatever is shown here, ISA extension, whatever multiplication, then comparison, floating point double, then you see vector, and then you see cryptography, and then facts entry, that is single instruction multiple data. All of them are extensions. Some of them have been ratified, some of them are still in the process of application. So what I am trying to say is that you can have a base design, and then you can choose which extension you want based on your application. So my idea in this talk will be for you to introduce when some of these extensions could be used and show that when you use these extensions, we get performance improvement. That's the idea of this talk. So we are going to look at these four last. First one is bit manipulation instructions, which are generally used for cryptographic applications. Means these are operations in cryptographic applications. There are cryptographic extensions also is part of the set, but that means that those instructions are more complex than bit manipulation. So we are just evaluating bit manipulation for cryptography here, and then we have vector and single instruction multiple data, which is available in x86 also. If you are aware of it, there are. So single instruction, for example, add 8 will add 8 bit 4, or based on how many lanes are there, how your implementation is, multiple additions of 8 bit will happen. So that's the difference between a scale up. So now the base processor will, if I refer to that, whenever I say scalar processor, it means it's the base processor, where when I say add x1, x2, x3, it means x2 plus x3 is equal to x1. That's the normal operation. Now if I say add 8, x1, x2, x3, then we know that individually registers are 32 bit, but I have 4 8 bits, right? So I am doing 4 8 bit addition. When I do add 8, x1, x2, x3, that's the difference. So this is a 4 addition is happening for 8 bits. In the other case, single addition is happening for a 32 bit. That's the difference between single instruction, multiple data, and a scalar instruction, normal instruction. That's what. So whenever I talk about Sindhi, we are talking about instruction space. So now these are the benefits. It's anybody can use it, and then it is modular. And if you want more features in your processor, you can use extensions and implement it, and you have the freedom to customize and add new instructions, because the instruction format leaves gaps for you to use encodings which are free for new instructions, which are not mentioned in the list that I have shown. That's also available. So and you can reuse different components again and again for based on what your requirement is. So these are the benefits. So that's why industry is going towards these. So guides. So here I'm just showing you what has happened in the industry. I hope I'm audible because so this happened from 2010 and testing were initially there. Then RB32 is the so then software, then it is software, space programs were running. And then hardware for IoT and SoC design, etc. happened. So it's fairly recent. In 2019, 2020 is where industry has started using this way ISA to come on and now we are in a state where people are working on more complex designs such as vector and more complex applications can be run. So initially when you look at it, it looks like a simple embedded processor kind of an ISA, but you can add these extensions and make it computer oriented and use for applications. Accordingly, what we are doing now is people have come up with software that supports this by ISA and complex systems are available nowadays. I have a slide which talks about where and what this is being used in industry. So sci-fi, hi-fi, premier, sci-fi is the company that is this is the big market people are using it. Then servers and cloud cloud servers are available based on this file. Mini laptops, the right hand side I have mentioned companies that are using based on this file. Mini laptops are there and lot of embedded companies are using now this file based microcontrollers or processors which are going on. So I know for sure that NXP is having main controllers system. That's what they showed in the presentation. Rest and all, you will have many subsystems are there, like complex subsystems are there. The main controllers system. So when I ask them why, they are telling that there are certain functions for which they will be able to customize. It's timing critical, and they will have an instruction itself to do that function, which will faster the execution rather than having an accelerator also. It will be there in the so I will talk about acceleration also so that you will have an idea of what happens when you run a program in a described PCB and described in an accelerator. I have a few examples. Whatever diagrams, whatever images are there are from the website of the company. There are more lists there, but I just mentioned few companies. I want to show that any of the products that are coming in the market. So, how do you categorize what you want for what based on domain? So, because I started off talking about extensions of demand and vector and PCB, I have shown applications that are used generally. Photography, then audio processing and routers, IT communication, etc. Basic kind of applications. Computer vision analysis and then AI/ML applications integrated using vector. So there are several applications and edge and sensor fusion and engineering etc. which will get advantage of all the things. So before going into that, I would want to just talk about what we mean by business architecture. So we know that you will be able to implement any task at different levels. The most common thing that we are aware of computing task implementing hardware is stable purpose. Any application program can run on this. That's very important. So the best advantage is general purpose. Whatever you want to target, you will be able to use that simple. But the problem because it is flexible, when flexibility is there, you don't have any constraints in the lower area or timing and etc. and power. So that's one implementation. At the other end, we are aware of SE there. You can have a dedicated hardware which is applications. You have a hardware that allows you to execute your program parallelly. Exploits data trackers and so not for all applications. For applications like what we discussed, XGA, DSP property, and another implementation is FPGA where you have a hardware which is programmable in nature. So and you map your application to the FPGA means the logic is already there. You just have to modify the logic to do your task. This one comes in between. The first two are off-the-shelf devices where you write application program and run your task. Second, FPGA as it, you will have to think about hardware which is going to, but which you should have to make sure the task is done. Again, as it means after designing the hardware, you come up with the chip. Whereas when you say FPGA, after designing the hardware, you map it to again programmable. That is the difference. So when you come up with all these things, you know that that all these things are possible because of Photoshop and as getting everywhere. You can look at what it says, and we have been very large. But we have come to a stage where small end of the line where there is no. So look at the performance and rolling biases. This one becomes stagnant because of limitations of because of the features that some so strong that companies are coming. And we have to think about what can you do. So we will have some of them. Domain-specific architecture is one thing. It is not general, but it is specific to the domain we are looking at. And when we tailor our hardware specific to our domain, we will be able to come up with a hardware which is efficient and power constraints. That's it. So this is from NSC and Patterson. So graph you will see what I want to show from here is that when you look at an addition operation, it is showing the energy as well as the area comparison for 8-bit, 16-bit, 32-bit, then floating point addition, floating point multiplication. When you look at it, area exponentially increases, right? With increase in area as well as energy. But if I am targeting a hardware for an audio application, then for a data application, I for sure know that my data points are 8-bit only. If you are looking at a great speed image also, you have only 0 to 55, right? Values. 8-bit values are only available, and if you are processing, if I am targeting a hardware for audio or video applications, my data will be restricted in size. But if I am running it in a general purpose system, my smallest size is 32 bit. And I will have an adder of 32 bit, multiplier of 32 bit, everything that is there for 32 bit. But actually, when I run the audio or video algorithm on top of it, I actually don't need it. I am wasting that. I have a hardware which is 32 bit running an 8-bit at the moment. So that's the point. So if I use 8-bit integers are 30 times energy efficient and 60 times media efficient. So now same thing happens for memory also. Access time versus area. Smaller, if I am going to store only 8-bit data, it will have smaller size then and access time will be faster. Based on both sides. The access time will be faster. So smaller memories are faster than we all are aware. Using these kinds of observations that are motivating the market to come up with designs which are tailored for a specific application, so that hardware is small in size, and because of this small in size, supporting the operations that you require, and it becomes energy efficient and when it becomes small in size, automatically it becomes delay and energy. So this is point that both already go for domain-specific architecture. So from all these flexible architectures, we are looking at architectures here which have efficient with respect to the task that you are doing. aim of so nowadays our systems are becoming more and more heterogeneous. Heterogeneous in the sense you will have one basic component followed by components that make the particular task faster, which could be single or multiple components. That could be in the form of an external accelerator or it could be in the form of instruction as such in the processor. When I talk about one main component, generally it will be an instruction processor only. So now you can have a specific logic inside the processor in the form of instructions, or it could be an accelerator which is external to the processor doing that particular task. These are the options that are available to you. So that's why we have the need for main specific architecture. And again I said extensions, when I talk about this file, come in the category where specialized instructions that allow you to do that. So now you see you have a base RB32I. I is integer instruction, and then you can which extension you want based on the original. When you come up with such a design, it will be efficient for that application. That's the aim of this. So generally, domain specific architectures are known as generally have reduced floating point operation based on requirement, and then they will have specialized memories near where you want the memories to be available, and narrow arithmetic logic keys will be there which allow you to implement. That is also a and processor performance is fast. And because of that, it will be basic. So standard processor followed by anything that asks for particular area that is getting, so that's what we are going to do. So these domains that we are looking for, we can do all these things are different areas, but for each of these areas you can tailor make the processor because of the modularity. So when you talk about domain specific architecture in the processor, that can be the special task can be implemented in the form of any of the following methods. So first method that we talk about, we all are aware of malicious accelerators. So if you are targeting model video processing, you are thinking about accelerators or AIML application. Think about CNN and then you decide your accelerator, and then you integrate it with your host GPUs in this case, and then using an AXI interface. And generally it is fast interface between the load and the accelerator. Run application using CNN hardware. That's you can have an accelerator or it could be a co-processor also. Whatever you do in your computer, you use a GPU and a host. GPU is actually a co-processor, and you know that GPU has its own instruction set. So whatever C program somebody has done it, whatever C program you write, you have to use something called CUDA and map it to your underlying hardware nowadays. Right now, the user only what he does, he installs a lot of packages in the host. It's actually a compiler which compiles your C program into something that can run in GPU and runs. That's how the actual running happens. So that is co-processor. So what Naresh talked about is an accelerator and GPU is a co-processor. That's the difference. You can go and in the voting further. Why is it different? It's good to know what is the difference between accelerator and co-processor. So those are, so you will have a basic host and either a co-processor or an accelerator which speaks the right. Then other than that, and because there was a lot about FPGA-based acceleration, I have just included FPGA. In both cases, whether I take an accelerator or co-processor, it is a chip for their task. But when you use FPGA and then you have a maybe PCI interface or an AXI interface in the FPGA, helping you to communicate with your code, then you can do any logic in FPGA by properly mapping the memory in the logic. So that's FPGA based. So it's a heterogeneous system, that's why I'm talking about. So you can have a core where you can have a co-processor. Floating point generally is like the co-processor. Intel has a lot of co-processor for floating point. GPU you can have, which is another co-processor. Then you can have an FPGA board also connected with suitable interface which allows you to run some application in the FPGA. This is how nowadays heterogeneous system will look like. Okay, and then all these things are additional logic which is outside the processor. So what I am going to talk about now is otherwise it's waste of using all these things. So because I know, then I will use that. And if it is embedded, generally we will use this. If it is embedded, I will use it. So an Arduino board, Arduino kind of microcontroller is actually it's more powerful than 32-bit. But if I am using it for some specialized application, I choose this. That's an example of ISA extension process class. And this quite gives you an optimal set of instructions that you can use for class. That's the advantage. So somebody has proven, analyzed, and come up with optimal set of instructions for class. So now you see the difference. How you can design an ISA for different things is what I want to highlight. I think in the next couple of slides I have some diagrams of so this is how whatever I have talked right now will go right, that is accelerator or processor stage, 4 stage, 5 stage, but operations are fetched in boards. Then access to memory or and then it is a co-processor provides set up. I'll say the time, right? So this is an example of, I just put an example which is there in my showing you how people have a complete add-on accelerator for this case is a member this AI in the application. This is something which is there. Data centers is available in data. So here what they have done, you see, they have a systolic current which speeds up matrix calculation. And then here use the PCI Express interface to connect to the systolic array, and all the other things are hardware around the systolic at the right time. So what will happen is this entire system, like I said, will be connected to a host computer, data center computer, and the job will be to put the system to the data center interface will be there. And I just wanted to go over this slide. So when you see where I put data and all other hardware and other the complex one. This is an example of so this may be the hardware that you use when you are running a website code. In the lab, you will so that's what maybe there in the diagram. So this is an example of the second phase where we have an FPGA and a host, and then we will so all these things are separate, and then we should have some action happening here. To do that, I just so these are all from some data. This is the diagram where see all the other previous slides your action was happening outside your pipeline. Here we have added an extension, a new user extension of this pipe. We are including that as part of the execution of the pipeline using instructions which are available. Adding new instructions here. It's not custom, it's extension level. So custom option is also available, and you are using something which is not there in any of the list. You just have to ensure that keyboard add is not the extension. That's all. So this is how you modify instruction. You can modify instruction set, add new, you can add new instructions, and then correspondingly extension. So how do you do it typically is what I want to show you this. There is an application that you are updating. You apply it and update ASM based on all subset instructions that are available. Identify which instructions are required for that application. Ensure that the hardware has been not all instructions. You have 4
the number of lines of code will decrease, memory readiness, storage reduces, and execution time also reduces. 100 lines of code reduced to 70 lines of code. Directly we give. So what they did is, for a particular application, we compile data without increasing processing. We saw that it was increasing. After seeing this observation, what we see is so this is showing you number of instructions. 100 10 other instructions are there and 104 instructions are there, and which corresponds to different kinds of AND or XOR, then shift operation, then carriers multiplications. All these things are different subsets of instructions. So what was done is we designed this is the algorithm implementation. So as a start, he designed it as a co-processor. This was connected to this is the processor here. Using a particular interface, we connected it as a co-processor. So it was not part of the pipeline. As a start, we started off with co-processor, and we were able to show that as a co-processor, also there is a lower rate of communication and scope of the communication itself internal benefits. Shakti board and they have an internal interface or scope. So when scope was interface, I have to choose the first one. So ESOP is the processor board that we use, and then it's a IT coupled processor. This is the interface that I was talking about. It's an handshake interface. And using it, we were able to see the performance improvement of 1.42 or certain applications. So this is using benchmarks. So how do you evaluate a processor's performances? Standard benchmark, standard application set is called a benchmark, and everybody who's working in the data use that benchmark and keep the performance numbers. Then you will be able to compare between different processors. If I run an A program, you run a B program, and then I say I take 100 cycles, you take 90 cycles, that's not a direct comparison. Frequency of operation also matters. So here, so generally what they do is, if I am looking at code size also, you use the same setup. Both of us run a application to be able to directly compare. That's why you will go on. So here they have used something called MBED, which is an embedded benchmark, and we find that there was so that means using big manipulation and running programs are beneficial for general purpose applications that we identified. So next step, what change was done is we integrated this into it's called regross into the execution interface. Previously it was outside the pipeline. Now we introduce it into the pipeline itself, and then when we evaluate the result, we see significant improvement. Showing with respect to base means they only use integer. So for the DMI, we were in manipulation, we were able to see speed search, general purpose application, middle applications, speed not there. Now, something that we observed it for certain or subset of instruction called serial, that is the instance of that was not there. But we know that for sure that is being used in the So next work, our next work, we targeted applications which use that particular instruction. Automatically, compiler suppose is not giving you instance of that. So next work, now particularly we have to ensure we look at that AES. In this case, AES is CPR, and CPR that's the first paper. Next set of slides we are going to look at ESP application. So what ESP application is when the person starts so here what is simply this is what is I just want to show. This is the scalar and repeated and this is the four loop where you are doing A plus B action and it's a loop of 4, right? So this is the scalar assembly code which will go through this loop multiple times. There is L1 here and you will go through this 4 times. But now perhaps in the instruction set has something called adding. So where you can add x10 plus x11 and x12 and here we are talking about each of these A and B as A and B operations. When you do this entire line of code is replaced by just one line. That's what I want to show you guys that this is how there will be code size reduction happening and that code size reduction can be directly translated to execution time. Right? Provided there is hardware for it. One adder of a regular size will not to have 4 8-bit adders. Right? Because this has to be supported. Right? So your hardware will have 4 different components to ensure that you take it addition. So this is what facts in the instructions will do. Adding is an example. That simply has add, subtract, shift, data movement, comparison, multiplication, all subsets which work for machine learning, speed coding, computation, all these things. Again, you are talking about this granularity of whether it's 4-bit, 8-bit, 16-bit, 32-bit data, you can work on. That's what these numbers do. This is the PCB extension. Pre-coding instructions are there in the language. This is just slide is showing you example of these applications and what kind of instructions are there. For example, add instructions are available for all are used for these kinds of expressions which are complex addition multiplication. Just for you to understand that dedicated instructions are there which can be complex way you write the code, and there were cases where he knew that this instrument should be used, they were not used, in the cases where we substitute. But we are substituting it is doing that function, we are changing our assembly code, but we have to ensure that it is doing the task. Change the this. But compiler plus substitution run to the you try to find the many of it you see, it shows that your compiler is not efficient enough to do this. നമ്മുടെ ചെയ്ത് കണ്ടുപിടിച്ചിട്ട് ഈ കമ്പൈലർ അത് അവിടെ എത്തുമ്പോൾ അല്ലെങ്കിൽ പിന്നെ നമ്മൾ റെസ്ട്രിക്റ്റഡ് ആണ് നമ്മുടെ റിസൾട്ട് കമ്പൈലറിന് പെർഫോമൻസ് അതില്ലാതെ ഈ കേസസിലൊക്കെ സബ്സ്റ്റിറ്റ്യൂട്ട് ചെയ്തിട്ടാണ് നമുക്ക് കണ്ടത്. ചെയ്ത ആൾക്ക് അതിനെപ്പറ്റി നല്ല ധാരണ ഉണ്ടെങ്കിൽ നമുക്ക് ചെയ്യുന്നില്ല. Adding that to those instructions. So now, next set of applications that we are looking at is AI, ML, and further. This support in this point of time easily available adding right. And Allah that this way of means support vector these both support data level analysis. So DSP onwards, what we are talking about is saying large amount of data going to process traffic. This is the basically by inherently or instruction multiple data processing. Vector is another piece. Which will allow where the number of operations are far than TCP. But the difference is that TCP is using existing registers to do the task. Vector link will existing registers. You have to come up with one vector register file that will support this kinds of data. Data processing will have data support. Data processors register. Number 32 registers TCP fine. But all of the time so you need a separate register file. Now that complexity is there in this. So in this, I'm just going to show how what is there in literature. Some works where people have used this 5 plus vector, this 5 plus so first one that is going to learn into the AI application. EDM for an open source compiler for neural networks. That means these are all jargons in that, but what it is doing is that it has come up with its own library for commonly used. The understanding is that they have their own library functions for functions that are part of the AI applications. The applications for the common library functions they will be using in this case PCP. PCP the company the difference using the functions which are commonly used in the application. Okay, now let's see. Now the program ഈ ലൈബ്രറിയിലേക്ക് പോയിന്റ് ചെയ്യുവാണെങ്കിൽ ഓട്ടോമാറ്റിക്കലി ആ കമ്പൈലർ ഈ ഫംഗ്ഷൻസ് വെച്ച് റീപ്ലേസ് ചെയ്യും. അത് ജനറേറ്റ് ചെയ്യുന്ന ASMൽ PCP ഇൻസ്റ്റൻസസ് ഉണ്ടാവും. എന്നിട്ട് അവർക്ക് ഹാർഡ്വെയർ ഒന്നും വേണ്ട. അവരെന്നിട്ട് കമ്പൈലറെ മോഡിഫൈ ചെയ്യും. എന്നിട്ട് അവർ അതിന്റെ നമ്പർ ആ പ്രോഗ്രാമിൽ എത്ര ലൈൻസ് ഒരു നോർമൽ വിതൗട്ട് PCP നല്ല ഡിഫറൻസ് ഉണ്ട്. എന്താണെന്ന് വെച്ചാൽ ഞാൻ നേരത്തെ ആനുവലി എന്നെ ബേസ് ചെയ്ത ഫംഗ്ഷൻസ് ഇതിന് ന്യൂറൽ നെറ്റ്വർക്ക്സ് സപ്പോർട്ട് ചെയ്യുന്ന PCP ലൈബ്രറിയാണ്. അപ്പോൾ നമ്മുടെ ജോലി എളുപ്പമാണ്. ലൈബ്രറിയിലേക്ക് അവരെന്താ പറഞ്ഞു കമ്പയർ ഔട്ട്പുട്ട് വെച്ച് അനലൈസ് ചെയ്ത് കിട്ടിയതാണ്. അതുപോലെ ഞങ്ങൾ റൺ ചെയ്തു അതുപോലെ വേറെ വീഡിയോകൾ സ്പൈക്ക് എന്നുള്ള സിമുലേറ്ററിലാണ് നമ്മൾ ഇവാലുവേറ്റ്. മറ്റേത് ഇവാലുവേഷൻസ് ആണ്, ഹാർഡ്വെയർ അല്ല. ബട്ട് ഇറ്റ്സ് എ മോട്ടിവേഷൻ ഫോർ ടു ഇംപ്രൂവ് ദി സിമുലേറ്റർ. ഞങ്ങൾക്ക് അങ്ങനെ വർക്കുണ്ട്, പേപ്പർ പബ്ലിഷ് ആവാറുണ്ടാകാം. But we have found that if I include recently and then run these applications on it, there is the simulation study പോലെ തന്നെ നമുക്ക് ഹാർഡ്വെയറിൽ കിട്ടിയിട്ടുണ്ട്. ഓക്കെ, ഇതിന്റെ ആഡ് ചെയ്തു. ഇത് സിമുലേഷൻ സ്റ്റഡി ആണ്. എന്താണ് ബേസിക്കലി ഈ ഫംഗ്ഷൻസ് എല്ലാം കൺവെർഷൻ ഫംഗ്ഷൻസ് ഇതെല്ലാം ഇതിന്റെ ആ ഫംഗ്ഷൻസിനെ മാപ്പ് ചെയ്യുന്ന and then you when you run that there is as high as 90% contribution fast, max coding rate. We see that there is performance improvement in each of the sub-tasks that are there. So what I am trying to say is we can be used to speed up without any additional hardware, without code facility, provided you have the software that you have. This is a real design that was done, which has the storytelling based. There is a vector unit to come down. Vector for the next extension. I said that AIML can be using these extensions content on the TCP and vector. TCP is an example on an vector. They are not included all instructions, but it's a real code and there is a comparison between vector is 5 and scalar is 5 and they are able to come up to 440x improvement, but at the cost of power and hardware. Vector is a more complex hardware. These are the ranges of the vector and other navigation. The pipeline then interface is proper, but it is not a common interface. It's not a common interface. So this is our where actually maybe inference currently and maybe market interface. There is another paper which was already done the evaluation between when you use vector and so it's not evaluation and maybe what is happening. They have base, which is we are talking about how it is. Then 78 supporting in it, 16 supporting vector and other configurations instructions. So vector 16, 32, 8 the versions of vector same instruction. Any type of operation supporting all that. That's what. So what is happening here? You see that this is verified over architecture and after then now you see the calculating the and what we see is that TCP to vector definitely vector improves more than TCP improvement. From base till CP and then vector 32 on based on input side but whatever it is, vector improves more than TCP. But at what cost on it? This area and this is energy and you see vector's energy is at some level and compared to CP, which is at higher level than CP. So when I am trying to consider an HT-wise energy is my concern, then and if it is an AI application, inference you are running, which will we choose? Speed ആണെങ്കിൽ നമ്മൾ വെക്ടറിനെ ചൂസ് ചെയ്യാം. അതിനും കൂടുതൽ എനർജി ആണെന്നുണ്ടെങ്കിൽ നമ്മൾ there is a difference provided time constraints is fine. അതിന്റെ requirement so that's the learning that I wanted to show this thing that that is compiler ഇതുവരെ ശരിയായിട്ടില്ല, but we find that DSP and HN our second discussion is supported and other supported AML option is PCP and vector. But then we are talking about simple workloads, area constraint from heavy workloads, PCP may not. So vector may be so vector is fast at the cost of നമ്മൾ ചെയ്ത പോലെ പ്രൊവൈഡ് ചെയ്തിട്ട് മോസ്റ്റ് ഓഫ് ദ റെഫറൻസ് സർവീസസ് യൂസ് ചെയ്യുമ്പോൾ ഒരു സാധനം പെട്ടെന്ന് തന്നെ ചെയ്ത് തുടങ്ങുമ്പോൾ അനലൈസ് ചെയ്തിട്ട് ചെയ്ത് തുടങ്ങുമ്പോൾ ആപ്ലിക്കേഷൻ സ്പെസിഫിക് ആയിട്ട് സംസാരിച്ചത് പക്ഷേ you will get an idea some references are
താങ്ക് യു മാം. പ്രോസസർ ആർക്കിടെക്ചർ എന്നതിന്റെ സാധ്യതകളെ കുറിച്ച് അത്യധികം വിജ്ഞാനപ്രദമായ പ്രഭാഷണത്തിന് ഈ സദസ്സിന്റെ പേരിലുള്ള ആത്മാർത്ഥമായ കൃതജ്ഞത രേഖപ്പെടുത്തുന്നു.
എഞ്ചിനീയറിംഗ് കോളേജിലെ ECE വിഭാഗം HOD ശ്രീകലാ മുഹമ്മദ് ഷിഫ്റ്റ്.
താങ്ക് യു മാം. ഞാൻ ശരിക്കും ഈ ഒരു സെമിനാറിന് വന്നതെന്ന് വെച്ചാൽ ഇത് വാണി സ്കീമിന് കീഴിൽ ലോക്കൽ ലാംഗ്വേജിന് അറേഞ്ച് ചെയ്യുന്ന ഒരു സ്കീമിൽ വരുന്ന ഒരു പ്രോഗ്രാമാണ്. ഇപ്പം ഈ സെമിനാർ FTP അല്ലെങ്കിൽ വർക്ക്ഷോപ്പ് ഒക്കെ എന്ന് പറയുമ്പോൾ നോളജ് ഷെയറിംഗ് ആണ്. സോ എനിക്ക് എന്തും ന്യൂ ആയിട്ട് ഞാൻ എടുക്കുകയാണ്. കാരണം എൻ്റെ റിസർച്ച് ഞാൻ കഴിഞ്ഞാണ്. ഈവൻ റിസർച്ച് എന്നുള്ളൊരു പ്രോസസ്സ് നമുക്ക് ജീവിതത്തിൽ ആസ് എ ടീച്ചർ നമ്മൾ എപ്പോഴും കണ്ടിന്യൂ ചെയ്യേണ്ട ഒരു കാര്യമാണല്ലോ. അപ്പം അതുകൊണ്ട് തന്നെയാണ് ഈ ഒരു വിഷയത്തിൽ തന്നെയാണ് ഞാനും ലോ പവറിലാണ് എൻ്റെ റിസർച്ച്. സോ നോർമലി ഐ ഇൻട്രസ്റ്റഡ് ഇൻ ദാറ്റ് പർട്ടിക്കുലർ ടോപ്പിക്സ് ആൻഡ് എനിക്ക് തോന്നുന്നു ഞാനൊട്ടും തന്നെ നിരാശ എനിക്ക് വരുന്നില്ല. കാരണം ഇവിടെ വന്നെടുക്കുന്ന ഓരോ റിസോഴ്സ് പേഴ്സൺസിനും കിട്ടുന്ന അറിവുകളാണ് അവർ ഷെയർ ചെയ്യുന്നത് അവരുടെ സ്വന്തം നോളജിൽ നിന്നാണ്, എക്സ്പീരിയൻസിൽ നിന്നാണ് വാട്ട് ദേ ആർ ഷെയറിങ്. സോ എൻ്റെ ഏരിയ ഈവൻ VLSA ആണെങ്കിൽ പോലും ഇത് എംബഡഡ് ആണ്. VLSA ആൻഡ് എംബഡഡ് ഈസ് ഓൾവേസ് റിലേറ്റഡ്. VLSAനെ പുറത്തോട്ട് കണക്ട് ചെയ്യുന്നത് എംബഡഡ് എന്നുള്ള ഒരു ടൈമിൽ വെച്ചിട്ടാണ്. അല്ലാതെ VLSA തന്നെ ഒന്നിനും തന്നെ നിൽക്കാൻ പറ്റത്തില്ലല്ലോ. ഇറ്റ്സ് ഓൾവേസ് ഡിപ്പെൻഡന്റ്. സോ ഈ ഒരു പർട്ടിക്കുലർ വിഷയത്തിൽ മാഡം പറഞ്ഞ പോലെ മാഡത്തെ കുറിച്ച് ഓൾറെഡി ഇൻട്രൊഡക്ഷൻ സാറ് തന്നു കഴിഞ്ഞു, കൃഷ്ണകുമാർ സാർ പറഞ്ഞായിരുന്നു. അതുപോലെ തന്നെ മാഡം ഇപ്പോൾ കവർ ചെയ്ത എല്ലാം സ്റ്റാർട്ടിങ് ഫ്രം റിസ്ക് 5 അതിൻ്റെ ഡൊമൈൻ സ്പെസിഫിക് ആയിട്ട് ISA എങ്ങനെ വരാം, അതുപോലെ തന്നെ ആപ്ലിക്കേഷൻ ബേസ് എങ്ങനെ ഡിസൈൻ ചെയ്യാം, അതുപോലെ തന്നെ ഒത്തിരി ഓപ്പൺ സോഴ്സസ്. സോ ഓൾ തിങ്സ് ഷീ ഷെയർഡ് ബേസ്ഡ് ഓൺ ഹെർ എക്സ്പീരിയൻസസ്. അതാണ് നമ്മളുടെ ന്യൂ നോളജ് എൻ്റെ ഒരു അഭിപ്രായത്തിൽ. സോ ഐ തിങ്ക് നമ്മളെല്ലാവരും ഇവിടെ വന്ന ആൾക്കാരെല്ലാവരും കുറേ പേര് റിസർച്ച് ചെയ്യുന്നതായിരിക്കും. അപ്പൊ നമ്മൾ ആലോചിക്കുന്നത് നമ്മുടെ ഏരിയ അല്ലോ, അങ്ങനെയില്ല. എല്ലാ ഏരിയയിലും ഇന്റർ കണക്റ്റഡ് ആണ്. തീർച്ചയായിട്ടും എനിക്ക് ഒത്തിരി കാര്യങ്ങൾ പഠിക്കാൻ പറ്റി. മാഡത്തിന്റെ വെരി ഇൻഫോർമേറ്റീവ് സെഷൻസ്. തൃപ്തി മാം from CUSAT. I also studied my MTech from the CUSAT, and really when I came here, കുറേ വർഷങ്ങൾക്ക് മുമ്പാണെങ്കിലും ഇവിടെ വന്നു കഴിഞ്ഞപ്പം CUSATന്റെ ഏരിയയിലൂടെ ഒക്കെ നടന്നപ്പോൾ എനിക്ക് വളരെ സന്തോഷമായി. ഇടയ്ക്ക് വരാറുണ്ടായിരുന്നു. ഇപ്പൊ കുറച്ച് നാളായി ഇങ്ങോട്ട് വന്നിട്ട് ഒത്തിരി നാളായി. അതും എനിക്കൊരു തീർച്ചയായും പുറകോട്ട് പോകാനൊരു ഇത് നൽകി. താങ്ക് യു ഓർഗനൈസേഷൻ ടീം. ഈ ഓർഗനൈസ് ചെയ്ത കോളേജ് മാനേജ്മെന്റ്, ടീച്ചേഴ്സ്, HOD എല്ലാവർക്കും കൺഗ്രാജുലേഷൻ. തൃപ്തി മാമിന്റെ ദൈവമായ താങ്ക് യു.
നമ്മുടെ ബഹുമാനപ്പെട്ട അതിഥിയോടുള്ള ആദരസൂചകമായി ഒരു ഉപഹാരം സമർപ്പിക്കുന്നതിനായി ഐസാറ്റ് എഞ്ചിനീയറിംഗ് കോളേജിലെ EC വിഭാഗം പ്രൊഫസർ ഡോക്ടർ ലൈല മാമിനെ ക്ഷണിക്കുന്നു. ഉപഹാരം സ്വീകരിക്കുന്നതിനായി ഡോക്ടർ തൃപ്തി S വാര്യർ മാമിനെ ആദരവോടും ക്ഷണിക്കുന്നു. ഈ മികച്ച സെഷൻ കൈകാര്യം ചെയ്ത ഡോക്ടർ തൃപ്തി S വാര്യർ മാമിന് മാനേജ്മെന്റിന്റെയും സംഘാടകരുടെയും പേരിൽ നന്ദി അറിയിക്കുന്നു. സെമി കണ്ടക്ടർ മേഖലയിലെ ഏറ്റവും പുതിയ പ്രവണതകളെ കുറിച്ചുള്ള നിരവധി വിവരങ്ങൾ പങ്കുവച്ചുകൊണ്ട് നമ്മുടെ ഈ സെമിനാറിന്റെ 1ാം ദിവസം ഇവിടെ വിജയകരമായി പര്യവസാനിച്ചിരിക്കുകയാണ്. അറിവും ഉൾക്കാഴ്ചകളും നൽകിയ എല്ലാ പ്രഭാഷകർക്കും അതുപോലെ സജീവമായി പങ്കെടുത്ത നിങ്ങൾ ഓരോരുത്തർക്കും ഞങ്ങൾ ഹൃദയത്തിന്റെ ഭാഷയിൽ നന്ദി അറിയിക്കുന്നു. കൂടുതൽ ആഴത്തിലുള്ള സെഷനുകളോടെ നമ്മുടെ സെമിനാറിന്റെ 2ാം ദിവസം